It might sound almost absurd, an explosion so vast it shattered forests, yet so mysterious it left almost nothing behind. No crater, no smoking meteor. Instead, it became a puzzle that stirred imaginations and fueled theories as strange as nuclear devices or even black holes. It's almost as if nature played a quiet trick, offering destruction without a trace. Tonight, with a little humor in our curiosity, we'll walk through how the mystery endured, and why its answers bring more peace of mind than confusion. Imagine yourself in a place where silence stretches far beyond the horizon, where the land itself feels endless. The forests are dense, the air is cool, and life moves slowly among the small settlements scattered across the Siberian wilderness. On that morning, nothing suggested that something extraordinary was about to happen. People stopped to gather water, chopped wood, or simply sat outside their wooden huts, completely unaware that the sky above them was hiding a secret that would soon break open with a force they could never have expected. For those who lived there, each day followed a rhythm familiar and steady. The taiga forest stood tall on every side, with straight lines of pine and larch trees towering like pillars, and the rivers ran smooth and constant. It was the kind of morning when nothing seemed unusual, but in an instant, without warning, the calm broke. A light cut across the sky, so bright and so sudden that it pulled people's eyes upward. It was described as though the atmosphere itself had been torn apart, leaving behind a wound that glared with fire. The light was soon followed by sound. A deep roar swept across the landscape, loud and powerful, not unlike thunder, but longer, rolling and mixed with something sharper. It was as if the heavens themselves were splitting open. People who saw the streak of brightness overhead had little time to process it before a shock wave reached the ground. In remote huts and open fields, men and women were thrown from where they stood or sat. The earth quivered, the air itself seemed to shudder, and heat rushed through the atmosphere so quickly that it burned to breathe. This was no ordinary storm or distant explosion. It was something entirely different, and the few witnesses who survived would forever remember that moment when the ground, the sky, and the air all seemed to collide at once. For many years afterward, their descriptions offered some of the only human records of an event that defied expectation. Unlike most skyborne events, which come and go unnoticed, this particular one had chosen an inhabited area, however sparse. That alone made the accounts all the more precious, for in history, it is rare that people are close enough to see such a cosmic event with their own eyes. Close your eyes for a moment and picture it. An immense flare separated the morning sky into two halves. The light gripped everything below, brighter than fire, brighter than lightning. Then, in the pause before the noise crashed down, there was an eerie quiet, as though time itself braced for what was next. Seconds later, the blast arrived, bringing with it a force violent enough to knock strangers to the ground miles apart. Trees bent and cracked, windows shattered, and animals scattered in confusion. Among the stories told later were details of burning sensations, as though invisible flames had brushed across the skin. Some remembered the terror of not knowing where the fireball had come from or what it meant. Was it a star breaking apart above them? Was it a weapon from some unknown source? To those living in isolation, far from cities and far from scientific explanations, the moment must have seemed almost beyond comprehension. And yet, despite the magnitude of what occurred, the pattern of damage raised new questions. Witnesses did not speak of the earth breaking open. They did not see a crater or a hole in the ground. Instead, they saw the sky itself flare and then collapse with sound and force. That detail became essential years later because it told researchers and explorers that the heart of the event did not come from below their feet, but high above, somewhere within the atmosphere itself. Few cosmic events ever offer us such clarity. We know of impacts from the past, preserved in stone craters, but we rarely have human eyes there in the moment to describe what it was like. Here, in this lonely region of Siberia, the voices of a handful of observers carried forward an immeasurable value. They told us not only what it looked like, but what it felt like. The sudden heat, the disorienting fall to the ground, the roar that kept rolling long after the light had gone. It is hard to imagine how disorienting it must have been to stand in a wooden cabin or open clearing, cut off from the rest of the world, and feel the sky itself trying to crush you down. The experience blurred lines between ordinary life and something that felt almost otherworldly. Many survivors wondered later what they had really witnessed. Was it a falling rock from space? Was it a flame of the heavens? Or was it something stranger, something the natural world had not yet revealed? This uncertainty only added to the mystery, and even now those moments remain preserved not only in science, but in human memory. It is one thing to measure energy release and shock waves. It is another to imagine the skin-tingling heat, the sudden fall as if pushed by unseen hands, or the flash so intense it could be seen across enormous distances. That morning, June 30th, 1908, marked a day when the cosmos brushed close enough that ordinary people could see it play out before their very eyes. And here lies the strange turning point. For as powerful as the blast was, as violent as the airburst cracked and echoed across continents, this was not the story of a crash into the ground. The witnesses did not run to a smoking hole. They never described a massive pit lined with melted rock. Instead, they remembered only the sky breaking apart above them. That single truth, that the destruction came from overhead and not from a direct strike on Earth, became the key detail that scientists carried forward. So, as much as this was an experience marked by fear and wonder, it was also one that left behind an odd, even uncomfortable silence. Because in the natural order of things, when something falls from space, we expect to find its scar in the Earth. We expect a crater, jagged edges, perhaps even fragments spread across the landscape. But here, on the edge of the Podkamanaya Tunguska River, the sky gave its show and the land bore the damage, yet the expected mark was gone. What happened in those few minutes was undeniable. The flattened trees and the seismic shock waves that rippled outward confirmed it. The eyewitnesses made it human, adding color and sound to the event in ways that measurements alone could not achieve. But in the aftermath, as researchers later began to piece together the truth, they faced a new and unexpected puzzle that the survivors could not answer. The Great Sky Fire had revealed one thing, that the phenomenon ended above the ground. But that brought everyone to a single haunting question that lingered over the empty forests and silent swamps. If something so powerful tore apart the air and flattened the earth, why was there no crater waiting to be found? Why would anyone expect a crater in the first place? It seems obvious. When something falls from space, the ground bears the wound. Stories of strikes on Earth had long been tied to great pits in stone and soil, places where the blow of a cosmic visitor was written directly on the landscape. So when word spread of the Siberian blast, people imagined the same. A vast hole in the earth marking the spot where the fireball had struck. It felt natural to assume that an explosion of such force must leave behind a physical scar large enough to be seen even from afar. Newspapers echoed this idea, shaping early images of the event around something like a meteor impact, simple and destructive, with a single center point where earth and sky had collided. For a time, rumor filled the gap. Some who lived far from the region told of a deep crater in the wild forests, though no one could actually point to where it might be. Others imagined molten ground, scorched black, and hardened into strange shapes. Because the site lay in such a remote, waterlogged land, decades would pass before anyone with scientific training could truly know the ground's condition. That delay allowed ideas to spread, and as they traveled, the expected story only hardened. There must be a crater. How could there not be one? Yet, as years stretched into decades, no trustworthy report ever confirmed the existence of any hole at the supposed epicenter. The absence became as puzzling as the explosion itself. In the 1920s, Leonid Kulik, a Russian mineralogist, gathered a small party and made their way toward the isolated wilderness. He had read scattered reports and was convinced that if a meteorite had caused such devastation, then fragments of it, and more importantly, its crater, would still be there waiting. For him, the chance to reach the Tunguska region carried not just scientific promise, but the feeling of uncovering something that had been locked away since the morning of the blast. Imagine the journey they faced. The forests of central Siberia were unkind to travelers. The ground was soft, often soaked with swamp water that pulled at boots with each step. Rivers cut across their path, and bridges were rare. Supplies had to be hauled by carts or slung across shoulders, and the insects of summer made even the simplest paws uncomfortable. Day after day, the team pressed on, expecting that their hardship would end in the reward of discovery. A massive depression, perhaps ringed with overturned earth, maybe filled with stagnant water, standing as silent proof of what had happened in 1908. As Kulik and his team entered the zone of destruction, they began to notice a pattern across the forest. Trees that stood tall elsewhere were here snapped and thrown across the ground, their trunks pointing away from a central area like the arms of a fan. For miles, this strange arrangement stretched outward, a clear sign of something violent. When they finally reached the place believed to be the center itself, the landscape was striking, but not in the way they had imagined. The trees were laid flat in radiating directions, and some stumps still stood upright with their tops sheared clean off. Yet the soil revealed no sign of impact. There were no great stones fused into glassy masses, no ring of crushed rock, and certainly no crater. The absence shocked them. The entire journey had been built on the expectation of a scar. To walk into that space and see only flattened trees, toppled in every direction, forced a deep reconsideration. How could an explosion so vast that it leveled miles of forest leave the ground beneath it untouched in this way? The contrast between their expectations and the reality before them became one of the most enduring mysteries of Tunguska. Take a moment to picture it for yourself. You spend weeks crossing marshland, enduring swarms of mosquitoes, feeling your body worn thin with the effort. In your mind, you are certain of what awaits: a crater, a hole big enough that you may peer into the Earth's wound and almost retrace the final moments of the cosmic body's fall. And then, nothing. Only trees pointing outward, like the spokes of a broken wheel, and silence. The missing scar is not only puzzling, it is unsettling. It suggests that the event you've come seeking did not follow the normal rules of impact. This realization pushed Kulik and later scientists toward a different explanation. If no object lay buried in the soil, and if no crater marked the ground, then perhaps the object had never truly struck the Earth at all. Instead, it must have disintegrated above, releasing its energy in the atmosphere. Such a burst high in the sky could spread its force across a wide circle, flattening trees without breaking open the land beneath. An airburst, not an impact. The airburst idea, simple as it may seem now, was far from the minds of most people in the early decades after Tunguska. Science had to catch up to the possibility. But there, in the flattened forest of Siberia, the absence of a crater pointed strongly to one truth. The destructive power had arrived from above, not from the soil. The ground had not been struck. Instead, the atmosphere itself had carried the explosion downward, pushing great waves of heat and force that extended across more than 2,000 square kilometers. It is worth thinking how this must have felt to Kulik himself, faced with such a strange result. On one hand, disappointment. No meteorite fragments to carry back, no grand photographs of a depression lined with shattered stone. On the other hand, wonder, because whatever had happened was new, and in that unfamiliar emptiness lay the promise of discovery. The missing crater was not a failure of the search, but a clue in itself. When word spread of his expedition's outcome, it fueled both interest and confusion. Some expected that hidden in the swamps or beneath the lake, perhaps, the missing crater still lurked undiscovered. Others began to accept more fully that what had happened was not a strike against the ground at all. For those who tried to imagine the event from afar, the image of flattened forest without a clear hole gave the tale an even more ghostly quality. Something immense had visited, but it left no body behind. The idea of an airburst would grow stronger with time, supported by more detailed studies. But in those early years, all anyone could agree upon was that the explosion had indeed come from the sky. The energy had released above the earth, scattering trees, but leaving the soil unbroken. For an event of such power, that alone was surprising. So, while the forests still stood silent, the question lingered. If the sky had carried the explosion, then where had the cosmic body gone? If the crater was missing because nothing ever reached the ground, then what traces, if any, had been left behind to prove that the visitor had been real? That question did not fade with the years. It only deepened, guiding researchers to examine not just the trees or the soil's surface, but the smallest particles hidden within the land itself. And it raised the more delicate mystery of what happens to the matter of a falling body when it bursts apart before reaching the ground. If no crater could be found, then the question became quieter, but perhaps even more puzzling. Did the sky's explosion leave behind any trace at all? Imagine walking through the same swamps, the same tangled trees, but this time not searching for the obvious scar of a crater. Instead, eyes turned downward to the soil, to the moss beneath your feet, to the dark, still waters of the marshes. The search is no longer for something dramatic and bold. It is for a kind of whisper, something small enough to be hidden in the very dust of the earth. The effort stretched on for decades, carried not by hope of great chunks of metal, but by patience to look for the faintest signs. As years passed, expeditions returned, and researchers walked among the forests again. They sifted through patches of moss, cut small cores of peat, and scooped black water from the swamps, each sample carried carefully for later study. They wanted to know whether the cosmic visitor had left hints too slight for the eye, hints not carried in great rocks or melted glass, but still waiting quietly in the ground. It was almost an exercise in listening, as though the land itself carried within it a faint secret, but one that only revealed itself piece by piece. At first, the results were disappointing. No matter how carefully they looked, they did not uncover the heavy fragments expected of a meteor. They did not find shards of iron buried in the peat, nor did they pull from the swamp any compact stony body. The land seemed empty of large relics, yet the absence itself pushed them to search with different tools, more delicate and precise. That was when the work shifted away from solid boulders and toward the smallest visible scales. Within the thin layers of soil, beneath the mosses and reeds, there rested particles so fine they could only be measured with microscopes. These were not large enough to be grasped by hand. They clung in dust, hidden until filtered and examined with care. Slowly, a pattern began to emerge. Mixed with the ordinary matter of Earth were tiny grains rich in silicate material and magnetic compounds. These combinations did not fit the ordinary background of the Siberian forest. They seemed to belong to something beyond it, as though slipped quietly into place from a source high above. The discovery did not arrive as a thunderclap. It was soft, like uncovering a faint footprint half washed away by rain. Yet to the scientists who worked with the samples, it carried the weight of confirmation. Something foreign had touched this land. These particles, so small they scattered easily in air or water, seemed like messaging crumbs left behind by a traveler who passed too quickly to rest. Imagine a stranger brushing through the taiga, vanishing in flame above, but letting fall a fine sprinkling of dust before disappearing entirely. That was the impression given by these tiny silicate and magnetic grains. For researchers, this was enough to shift direction. Even without the dramatic find of a crater, they now had matter that clearly did not belong to the forest alone. It was extraterrestrial, faint but clear. Without rushing, they came to see that these grains matched best with the image of an incoming body breaking apart in the atmosphere. In that scenario, the object did not survive as a whole to strike the Earth. Instead, it fragmented and vaporized with such violence that little could remain. Only the smallest shards of its composition made their way down, settling with the dust and rain into the layer of peat. The soil told this story gently. Layer upon layer, one could read the past of the forest in its annual buildup of growth and decay. And there, fixed in the strata corresponding to the year of the explosion, the unusual grains appeared. It was like finding a foreign thread woven into an otherwise local fabric. The placement confirmed that they were not a later intrusion. They belonged to that year, to that moment, to that massive event when the sky unfolded upon the wilderness. It is easy to imagine disappointment in not finding bold fragments, glittering metallic rocks that could be displayed as trophies. But in their absence, the dust itself gained a quiet authority. These microscopic clues became the heart of the evidence, the bridge between human memories of fire in the sky and the physical cause that created it. Without them, Tunguska might have remained suspended as only story and speculation. With them, the mystery stayed alive, but found an anchor in hard detail. Think of it as a balance in scale. On the one side, the destruction was vast. Countless trees knocked down, shock waves felt hundreds of miles away. On the other, the physical evidence was almost invisible, measured in specks that could rest unnoticed on the tip of a finger. Yet that contrast is what gave strength to the explanation. Large ruins were never found because the body itself never met Earth as a whole stone. The dust told us that what survived of it was only what could remain suspended long enough to reach the ground without fire consuming it completely. These discoveries guided thought back to the airburst idea. The absence of a crater, once such a frustrating gap, now touched hands with the presence of cosmic dust. Put together, they revealed a clear pattern. The event had unfolded above. The cosmic object had screamed into the sky, where pressure and heat shattered it entirely. What then reached Earth was only force, downward blasts of energy, and faint dust that fluttered to the ground long after the roar had passed. This was not a dramatic fall of a single stone. It was a disintegration ending in countless sparks and particles dispersed into thin air. And here lies something almost poetic. The forest still carried the scars in its pattern of flattened trees. The soil beneath still carried the faint shimmer of materials, not its own. In time, the trees regrew, and the ground covered over with moss and ferns. But within the layers of dirt, that faint reminder remained. It was as if the earth itself had tucked away the smallest fragments of the story to hold them safe as generations of people walked on. The insight mattered because it linked Tunguska to a wider cosmos. Without those grains, the event could have been explained in countless imaginative ways, some even speculating on unreal possibilities like antimatter or artificial explosions. But with them, the narrative pressed closer to the ordinary paths of asteroids and comets. The evidence was not dramatic in size, but it was faithful in character. Matter from beyond Earth was indeed there, even if it was measured in dust instead of boulders. This is how science sometimes works, through patience rather than spectacle. Great craters are easy to see. Tiny silica-rich specks are not. Yet in this case, the quiet method of dust collection provided the stronger proof. Without ever holding a meteorite fragment, researchers could still show that something cosmic had arrived. As you imagine the still air above those swamps, picture the tiny grains drifting down, unseen and unnoticed by anyone alive at the time. They passed through the smoke, through the haze, through the sounds of trees falling and animals running in fear. Settle in at last, they joined the slow accumulation of peat, where, decades later, they would be discovered and recognized for what they were. In their absence of size, they carried significance. And so the Tunguska story shifted once again, from the grand vision of a massive crater to the more delicate reality of dust. Instead of a hole to mark the blast, the Earth carried its trace in hidden particles. They became not only clues, but the only solid footprint of the visitor that morning. Stronger than rumor, stronger than speculation, they grounded the mystery in real, physical detail. But as is often true in such puzzles, each answer unlocked a new question. If the cosmic traveler left only dust behind, what kind of body was it? Was it a rocky asteroid so brittle that it fractured entirely, shattering in the pressure of the atmosphere? Or could it have been an icy comet, its frozen form vaporizing completely in the heat and leaving almost nothing but vapor and cloud? This new thought began to gain attention, carried as gently forward as the dust itself, inviting reflection on whether the greatest blast of modern history was born not from stone, but from ice. Could the answer to Tunguska have appeared not in the wilderness itself, but far above it, lingering in the night sky across an entire continent? After the morning when Siberia shook, another quieter signal drifted into human notice. In the weeks that followed, people as far away as London and beyond began reporting something unusual. The skies at evening shimmered faintly, glowing even after the sun had set, soft enough to be strange, yet bright enough to make reading outside possible long into the night. It was as though light that should have faded had found a way to return, dancing in twilight with a pale, ghost-like brightness. This delicate glow did not fade quickly. Through much of Europe, observers wrote that something about the atmosphere itself had changed. The glow stirred questions. It did not look like the northern lights, which rose as curtains of shifting green and red. It was a calmer, steadier gleam that seemed woven into the sky itself. The timing was impossible to ignore. The Tunguska blast had unfolded on June 30th, and only days later these glowing nights began. In those days before satellites and modern climate science, people turned naturally toward cosmic explanations, and one in particular began to stand out, drawing new life from each faint shimmer in the summer night. Comets had long carried a reputation for leaving streaks of light, for trailing dust in their path as they swept past the Earth. These icy travelers crumble easily, shedding particles by the ton, which may drift across the atmosphere for weeks or months. Known to be fragile, built more from ice and softer rock than solid metal, comets seemed a perfect match for what Tunguska had displayed. Colossal energy in the sky, yet no crater on the ground. If an icy nucleus had shattered in the atmosphere, it could vaporize nearly cleanly, leaving only vapor, dust, and invisible gases to scatter above the forests. That dust, carried higher and wider by winds, might have been the very cause of those luminous nights drifting gently across Europe. Let's take a moment to imagine what this reasoning would have felt like in the early decades of the 20th century. Scientists stood before a mystery, where trees lay broken for miles, where witnesses recalled blinding light and immense heat. Yet no crater, no obvious rock, and no metallic fragments lay beneath the soil. Then word arrived that far-off skies had glowed strangely in the aftermath, enough to be noticed by those who had no connection to Siberia. Linking one with the other carried a kind of elegance. If a comet had dissolved in the air, it could explain both puzzles at once: the lack of fragments and the curious sheen that appeared in nighttime skies. This idea carried a gentle beauty, because comets often inspire both awe and mystery. Unlike asteroids, which are commonly thought of as dry boulders, comets appear in the human imagination as icy apparitions, streaking across the firmament with tails that shimmer for everyone to see. Their fragile structures seem capable of producing exactly what Tunguska displayed: destruction without a hole, dust without stone, light without fire on the ground. The hypothesis attracted interest because it answered more than one question at once. It promised a simplicity in a sea of confusion, tying together the violence of Siberia and the glow over European towns. The science behind this glow has its own quiet story. At very high altitudes, where the air is thin and cold, faint clouds sometimes form. These are noctilucent clouds. They do not shine from within. Instead, they act as gentle mirrors, catching sunlight from beyond the horizon and scattering it back to Earth long after dusk. In 1908, people marveled at skies that gleamed so strongly they seemed unnatural, as if stars had multiplied with living light. Cometary dust offered one possibility for creating such clouds. If countless particles had been released into the upper atmosphere by the Tunguska explosion, they might have formed tiny surfaces for ice crystals to cling to. Those ice-coated particles would reflect light more efficiently, producing the eerie glow reported across the continent. The comet hypothesis also gained strength from comparison to known comets. Records from the centuries showed how some comets lost mass rapidly during solar approaches, spewing dust and gas into the void of space. Such bodies were believed to be fragile, likely to fragment dramatically if they entered the dense layers of Earth's atmosphere. To some researchers, Tunguska sounded exactly like such a scenario. A small, icy comet, no more than 100 meters across, meeting its end in a sudden, heated breakup well above Siberia. The violent transformation would yield a massive explosion in air density, scattering energy and dust across the region, but leaving no large boulders to recover afterward. But even as the comet idea spread, cracks began to show. Expeditions to Siberia looked for remnants, for any sign that icy matter had reached the ground, or that chemical signatures unique to comets remained within the soil. Yet, for every careful test of peat samples, the results showed only microscopic silicate and metallic fragments, more often linked with rocky material. If a comet had been the culprit, there was an expectation that traces of volatiles or icy chemistry might appear. None did. The dust found did not whisper of frozen cores. It hinted more toward fragmented stone. Still, the idea had a resilience. A comet offered a graceful path to understanding why Tunguska had left no crater and why skies far away shimmered strangely after the event. It explained how something could release such energy without leaving stone across the taiga. For decades, the comet hypothesis walked side by side with the asteroid explanation, supported by its charm, even if weakened by its missing evidence. People found themselves drawn to it, not only for its science, but because, like a comet, it radiated a certain wonder. It allowed the mind to imagine a sublime object of beauty, becoming, for a few seconds, an agent of destruction. As you listen, let your mind rest on that contrast. Devastating force in Siberia, paired with calm, glowing nights in Europe. Could one event, both violent and quiet, be born from the same icy wanderer? For many, the symmetry was difficult to resist, and in the absence of absolute proof, elegance can shine almost as brightly as truth. Yet despite its attractions, the comet's scenario never managed to cross from plausible to proven. Each expedition returned without frozen remains. Each test, though revealing unusual dust, found more evidence for rocky composition. Without direct material from a comet, the idea remained what it began as, a hypothesis, not a certainty. Researchers recognized that it explained some puzzles, but left others unanswered. Take a deep breath here and let that fact rest for a moment. The mystery lingered not only because answers were partial, but because each possibility seemed to carry its own poetry. A comet, ephemeral and fragile, would have dissolved gracefully before reaching the Earth, leaving only glows in the night sky and flattened forests as its testament. That image stood against the asteroid model, blunt and solid, which suggested matter more ordinary, but still capable of extraordinary damage. Balance between these two views stretched long into the century. What keeps the comet idea alive is its beauty. Even without support, it continues to appeal to the imagination more than a stony asteroid does. People think of comets as messengers, carrying bright tales across the heavens. Linking one of those visitors to Tunguska transforms the event into a rare, almost poetic collision between beauty and devastation. But science presses for more than poetry, and without clear cometary substance at the blast site, the theory remains incomplete. Questions about Tunguska lingered for decades beyond the confirmations of dust and soil. Some researchers leaned toward rock, others toward ice. Some accepted both as possible. But the comet idea always stayed close at hand, nourished by the sheer fascination it offered. And in the years when information was thinner and tools less precise, its hold on the imagination was strong. Over time, though, every elegant explanation faces scrutiny, and the comet hypothesis often wavered under that weight. Nonetheless, the mystery of luminous skies is real. The glow across Europe remains a reminder that the blast touched more than Siberia. It reached into a larger atmosphere, changing how nights appeared for thousands of people. That fact alone gave rare reach to an event born in an isolated swamp. So, the comet remained a tempting possibility, attractive, capable of explaining the glow, yet forever weakened by missing proof. It sits in the history of Tunguska like a half-remembered dream, persuasive but not solid. And as long as conventional ideas left gaps, imagination felt free to wander toward even more unusual answers, proposals that stretched beyond expected science, hoping to explain an event that had shaken both Earth and sky. When events defy simple explanations, the human imagination often begins to stretch outward, reaching for ideas that step beyond the ordinary. The Tunguska blast, with its missing crater and disturbing force, provided soil for such speculations to grow. For many, it felt uncomfortable to accept devastation without a clear physical remnant, so theories spread that leaned less on what was known and more on what was possible. In the middle years of the 20th century, with new discoveries in energy and physics suggesting powers once unimagined, the absence of a crater gave space for imaginations to build bold alternatives. Let's picture those years for a moment. The world was beginning to measure energies on a nuclear scale, testing bombs whose fireballs lit desert skies. Scientific talk turned often to matter and antimatter, to forces hidden within the smallest particles. Black holes moved from abstract equations to entities spoken of as if they might exist near us. Within such an atmosphere of curiosity, it felt possible, even natural, to link an unexplained blast in remote Siberia with new, radical ideas of cosmic power. People were willing to layer fresh speculation upon the bones of mystery. So exotic interpretations began to rise. Some whispered that perhaps the Tunguska blast had been caused by antimatter colliding with matter. In that concept, a small chunk of antimatter, drifting like any natural body through space, might have entered Earth's atmosphere. Antimatter, when meeting normal matter, annihilates on contact. Even a small mass could release energy far beyond what chemical or nuclear explosions offered. It sounded like a perfect fit for the Tunguska record. Enormous energy set free, but no physical remnant left behind. The appeal was easy to see. Where better to test such an exotic possibility than an event that had already escaped usual explanation? Others imagined nuclear forces at play. By the middle of the 20th century, human beings had seen cities destroyed through nuclear fire, had measured fallout drifting across broad landscapes, and had begun tallying the invisible toll of radiation. To interpret Tunguska through that new lens was tempting. If, in 1908, something like a nuclear device had detonated above Siberia, it could explain the blast's magnitude and its spread of heat without creating a typical impact crater. Some even wondered if the event might have been artificial in origin, though most serious speculation stayed within the boundaries of natural processes. Still, the nuclear image settled strongly into imagination, marrying the known results of a bomb with the mystery of a missing rock. There were also ideas that stretched still further. A tiny black hole passing near or through Earth was one such suggestion. In such visions, Tunguska represented not an asteroid or a comet, but the fleeting brush of a deep space phenomenon. A black hole, so small it might be undetected, sweeping across our planet and releasing energy as it interacted with the atmosphere or exited through the opposite side. While the mechanics of this were complex and uncertain, the idea carried a strange allure. To think that the Siberian forests had been flattened not by stone or ice, but by the whisper of a cosmic singularity, was a picture that stirred the imagination in ways more concrete explanations never quite matched. As you listen to these theories, take a deep breath and set aside the impulse to dismiss them right away. Each, though unlikely, reflected an underlying need to make sense of something extraordinary. When witness testimony speaks of blinding light, searing heat, and thunderous sound, but the ground refuses to show a crater, it makes sense that people would lean into other paths of thought. These exotic interpretations became like stepping stones in a fog, temporary places to rest. Curiosity until clearer ground appeared. The nuclear explanation carried its own problems. If a device or reaction of such scale had detonated, radioactive signatures would be expected, subtle fingerprints written into the soil and lingering in the forest. Yet, as decades passed and scientists gathered samples of peat, water, and earth, no such radioactive traces appeared. Without fallout or lingering radiation, the nuclear likeness fell away. It could produce the right image of energy, but the evidence stubbornly refused to align. The antimatter idea faced its own challenge. Because annihilation between antimatter and matter is absolute, it leaves behind not dust, but specific byproducts, radiation bursts that would have found their way into more lasting signatures. No such desolation of invisible particles or radiation showers marked the site. And so, even though the neatness of energy without fragments had lured thinkers for a time, the footprints did not match. The hypothesis began to fade into the realm of interesting, but unsupported, thought experiments. As for the black hole theory, it seemed dazzling precisely because of its strangeness. Yet, when examined closely, it demanded consequences that had not happened. If a micro-black hole had pierced Earth, one might expect an exit wound, another region of devastation elsewhere halfway around the planet. None existed. The simplicity of describing Tunguska's missing crater with such a compact celestial body quickly met the harsh resistance of missing data. Once the spell of wonder lifted, the odds of a wandering singularity clipping Earth in 1908 began to seem vanishingly small. These exotic ideas, though fading, served as stepping stones in the broader journey of understanding. They remind us of a deeper truth about human nature. When faced with mystery, we often reach first toward imagination. And even when these imaginative stretches are proven wrong by evidence, they hold value in showing the range of ways people will try to fill silence with meaning. To say that exotic theories faded is not to treat them as useless. Rather, they enrich the conversation, making more ordinary asteroid explanations feel earned and tested by opposition. Let's take a moment to reflect on that. The absence of a crater had pressed the mind toward extremes. It invited antimatter, nuclear fire, or black holes as scaffoldings to hold up the enigma. And though each eventually failed against observation, the willingness to imagine them speaks powerfully to the human habit of exploring what feels possible in the absence of certainty. These ideas enrich the mystery, turning the Tunguska blast from a simple puzzle into a broader reflection on how science and imagination intertwine. As evidence grew stronger for conventional explanations, dust particles in soil, patterns in tree damage, and more refined models of airbursts, the need for exotic guesses fell away. By the close of the 20th century, most serious scientific work had shifted firmly back toward asteroid physics. The strange whispers of antimatter and black holes became faint, lingering more in the background of public fascination than in the pages of active journals. While popular culture sometimes still invoked them, science itself had largely followed the path of evidence back into the realm of known bodies, stones and ice falling from space. This, in a sense, is part of the quiet rhythm of discovery. At moments of uncertainty, the imaginative range stretches from the plausible to the bizarre. As knowledge accumulates, the wide net narrows. Antimatter and black holes were part of that range, creative but unsuccessfully tethered to reality. What remained at the end was not exotic in appearance, but still extraordinary in scale. A natural body from space, shattered in Earth's air, releasing energy on a scale comparable to nuclear devices, yet belonging entirely to the paths of asteroids and comets. And so the story of Tunguska carries not only the power of a cosmic event, but also a window into how people seek to explain mystery. Even in failure, exotic theories remind us of the creativity curiosity can inspire. They are like trails explored and then left behind, valuable for how they open new perspectives, even if they lead to no final treasure. Over time, though, attention shifted again toward the land itself. Because just as science seemed to close the door firmly on the stranger speculations, one more feature near the Tunguska site appeared to reawaken the debate. A hidden lake, quiet and narrow, called forth new excitement. Could this be the crater that had always been missing? Could it prove that at least a fragment of the cosmic body had reached the ground after all? What if the missing crater from Tunguska had been there all along, hidden in plain sight beneath still water? Imagine walking through dense forest and swamp, and at the edge of this wild landscape, you find a narrow lake, quiet and long, stretching like a tear in the earth. Its name is Lake Checo, and for decades it was nothing more than a lonely feature on a map. But in the early 2000s, it stepped into the mystery as some began to wonder whether this peaceful body of water was not natural at all, but instead the buried mark of the Tunguska blast. An expedition from Italy set their focus on Lake Checo, looking not at the surface, but beneath it. They carried sonar instruments to scan the shape of the floor below the water. What they saw pulled them closer to the idea that this lake might have been formed in 1908. The basin beneath the waterline did not have the shallow, rounded shape many lakes carry. Instead, its structure looked more like a funnel, narrowing as it went downward. To an eye searching for impact signatures, this form appeared oddly artificial, as though carved by something that had struck from above with great velocity. It carried a geometry that suggested sudden creation, not the slow erosion of centuries. Layered into this puzzle was the story told in the mud itself. Sediment on the bottom of the lake did not appear to stretch back into many centuries, as might be expected of a natural, older body of water. Instead, the records from the cores taken by the expedition suggested fewer layers, more recent in origin. That hint folded neatly into the possibility that the lake might not have existed before Tunguska. If this were true, then when the blast occurred, perhaps a fragment did survive, crashing down to scoop out the hollow that slowly filled with water. To the scientists who gathered this data, the lake's youth stood as a powerful clue. Picture the excitement this must have stirred. For nearly 100 years, people had hunted for a crater and failed to find one. Then, suddenly, a lake within range of the epicenter suggested a different story. Instead of staring into endless forest with no scar, researchers could now place a finger on a map and say, "Here is something." The sense of hope was palpable. After decades of uncertainty, perhaps this stretch of water, untouched and quiet, carried within it the last trace of the sky-born object. Imagine the relief in thinking that a missing piece of the puzzle might finally be sitting in still water, only waiting for modern tools to reveal it. But as is often the way with mysteries, others looked at the findings and saw different answers. Some geologists argued that Lake Checo was no sudden creation at all, but simply a natural feature that predated the Tunguska blast by centuries, perhaps even millennia. They pointed out that rivers in the area might have carved such a space, leaving behind a depression that filled naturally. They read the sediment not as new, but as more complex than first measured. In their view, the Italian expedition had fallen into the trap of fitting results to match expectation. The lake, they said, was simply old, ordinary, and unrelated to the morning when Siberia shook. This counterargument introduced a sharp pause. If Lake Checo had always existed, then its shape and sediment were only deceptive coincidences. The funnel-like structure might not reflect impact, but instead reflect processes of erosion and deposition unique to that land. The fewer sediment layers might represent deposition rates that changed with conditions, not disappearance of centuries. To those who held this line of thought, the lake had been wrongly swept into Tunguska's orbit and needed to be placed firmly back into the category of natural formations. Yet the debate did not end there. Supporters noted that Lake Checo did not look quite like other lakes in the region. Its narrow, elongated profile gave it a form more reminiscent of small craters known elsewhere. This impression alone was enough to keep the door open. It was too unusual to dismiss out of hand, and too aligned with the blast's vicinity to ignore fully. Whether the lake had truly been born in 1908 or not, its peculiar shape demanded continued curiosity. The discussion came to reflect the deepest challenge of Tunguska. Answering in absolute terms remained elusive. Each piece of evidence brought a mixture of clarity and ambiguity. Sonar maps painted one picture, sediment cores another, professional disagreements still another. The result was not a conclusion, but a continuing circle of ideas. For the wider public, this meant the mystery endured, inviting people to imagine fragments of the cosmic body still buried beneath the muddy bottom of Lake Checo. For scientists, the debate underscored the difficulty of reconstructing the past when all signs are subtle whispers and nothing is obvious. Let's take a moment here and imagine two versions of the same landscape. In one, the lake predates the blast entirely. It lies quiet, filled with water from melting snow and rain, its banks lined with moss as they were centuries before. Tunguska comes and goes, flattening trees for miles around it, yet the lake itself does not change. In this story, Lake Cheko is simply an observer, unchanged by the event. In the other version, Tunguska's energy tears above the forest, and as fragments break, one piece crashes into the earth, digging a sudden hole in the swampy soil. That hole fills over time with water, becoming the lake that now deceives the eye with its age. To separate these stories fully is a challenge, and that difficulty is why the debate remains so alive. This is the sort of puzzle that does not necessarily need to be solved to hold fascination. The very possibility that Lake Cheko could be the missing crater keeps curiosity ignited. It rests quietly in the wilderness, not offering direct confirmation, but never denying the speculation either. Every sonar map and core sample seems to sharpen the tension rather than resolve it. For those who imagine the event, the idea that beneath its waters rests a fragment of the Tunguska body gives an evocative picture, one that connects the forest destruction to an actual physical remnant of the visitor. And yet, others remind us gently that the absence of certainty does not equal proof. To point at the lake and declare it, the crater is tempting, but evidence does not uniformly agree. Instead, the deeper message may be that Tunguska resists easy answers. Even when we think we have found the missing piece, new studies bring it back into doubt. It is this repeated cycle of hope and reconsideration that defines the history of Tunguska research. Lake Cheko fits neatly into that rhythm, neither confirmed nor erased, living in the space between possibility and skepticism. In the broader scope, the lake serves as a mirror of the event itself. Tunguska flattened trees but left no crater. The mystery invites questions but rarely gives final answers. In that sense, Lake Cheko is almost symbolic of the entire story, half convincing, half elusive, holding attention without granting closure. Its debate highlights how science grows not only from certainty, but from careful disagreement, from multiple perspectives pressing against each other until better tools can move the line forward. So while some groups remain certain that Lake Cheko long predates the event, others continue to hold the idea that it hides a fragmentary crater beneath its waters. This tension has not been resolved, nor does it immediately need resolution to sustain interest. For the vast wilderness of Siberia does not speak quickly, and its quiet lakes are patient in their secrecy. Take a deep breath and let your mind pause on that image. A narrow lake in an endless forest, quiet, untroubled, but carrying within it the possibility of being the only true scar from Tunguska. Whether natural or extraordinary, it carries the weight of curiosity that a century could not erode. This is why, even as other theories have faded, Lake Cheko continues to be spoken of as a potential key. It may never reveal itself fully, but the very act of searching has deepened the mystery's appeal. And while disagreements remain, that is not failure. It is the very essence of how questions endure. Yet as arguments circled in journals and conferences, the wider scientific world began to bring in sharper tools, ones that could model the event itself and cast new light on how such a blast could occur from the sky. Modern computers, inspired by later airbursts in our own time, began to redraw the Tunguska picture in ways that no lake, crater, or fragment alone could. And in those simulations, the forest's destruction and the missing crater finally seemed to find balance in an answer far more direct. How did scientists finally draw together all the scattered pieces into one picture that seemed to make sense? For more than a century, Tunguska stayed suspended in a mist of theories, asteroids, comets, even ideas that reached into science fiction. But in recent years, with powerful computers and the ability to recreate events in digital form, researchers began to trace the moment back with new tools. And when they did, the old disagreements about craters, fragments, or glowing skies gave way to something much simpler. The picture that emerged from modern models was steady and focused. Tunguska was not strange at all, but rather an enormous version of a kind of event we have actually witnessed in our own time. It was the 2013 explosion over Chelyabinsk, Russia, that reminded the world how real and how recent these skybursts can be. Imagine yourself standing in a modern Russian city on that cold winter day, when without warning, a fireball brighter than the sun streaked across the sky. Every camera caught it, dashboard cameras in cars, security footage on streets, even mobile phones lifted in surprise. Just seconds later, a powerful shockwave followed, blowing in windows, injuring thousands, and startling millions more. Yet when people rushed outside to look for a crater, they found none. This time, with video records and real-time monitoring, scientists had the rare chance to study precisely what had happened. The Chelyabinsk event became a living laboratory, showing that a solid but fragile asteroid could explode high in the atmosphere and unleash energy across a wide region without striking the ground. The parallels with Tunguska were striking. Here, in the 21st century, we finally had something close enough to record and measure. That was the missing piece researchers needed. Armed with thousands of modern observations, they turned their attention back to 1908, asking a simple question. Could Tunguska have been nothing more than a larger cousin of Chelyabinsk? For a long time, the numbers surrounding Tunguska shifted dramatically, because without agreement on height or size, estimates of energy went in every direction. Some early guesses placed the explosion only a few miles above Earth. Others suggested it happened far higher, tens of miles overhead. The energy estimates varied too. Some declared the blast equivalent to a few megatons of TNT. Others suggested many tens of megatons. Without details, the story could bend whichever way a theory preferred. But what the Chelyabinsk data supplied was precision. And with that precision, scientists at NASA in 2019 used modern simulations to apply the same techniques backward to the Tunguska blast. The models recreated what a stony asteroid would do when entering Earth's air. Unlike ice-rich comets, a rocky body can endure higher pressures before breaking apart, but once the stress passes the rock's strength, it shatters explosively. The computer models captured how heat, air resistance, and fragmentation interact. They showed the Tunguska body was unlikely to be a comet at all, but instead a compact rock about 50 to 80 meters across. Entering fast, it exploded violently while still high above the taiga, roughly 6 to 9 miles in the sky. That height was low enough for the shock wave to slam into the Earth with devastating force, but high enough that the asteroid itself never touched the soil. This conclusion balanced the puzzle pieces in a way older theories never could. The absence of a crater was accounted for because the body had fully disintegrated before touching the ground. The pattern of trees radiating from a central point matched because the shock wave rolled outward in all directions. Even the seismic waves logged on instruments across continents could be matched with the energy release predicted by the computer. What had once felt like fragments of contradictory facts now fit together in a clean, sharp picture. The energy numbers were sobering too. The simulations suggested between 10 and 30 megatons of explosive energy, hundreds of times stronger than the bomb dropped on Hiroshima. To hold that scale in mind, imagine a weapon powerful enough to destroy a city, unleashed not by people, but by nature, and not in war, but in silence above a remote wilderness. In 1908, no one had even conceived of such energy in human terms. Today, we can measure it accurately and know that the blast released more power than the largest bombs of the mid-20th century. Let's pause on that idea for a moment. A rocky asteroid, not huge by cosmic standards, no larger than a small city block, entered the atmosphere and disintegrated. Its power was measured in megatons, its destruction sweeping across some 2,000 square kilometers. And all of this happened without leaving behind a single whole fragment large enough to collect. The Earth absorbed the wave of energy, the forest fell, the soil trembled, but the stone itself vanished in heat and shrapnel long before reaching the ground. You can almost sense the relief of scientists who had pressed against confusing evidence for decades. At last, the models balancing size, height, and energy came together neatly. It was not exotic matter, not a comet dissolving completely, and not a fragment hiding beneath Lake Checo. It was simply a stony asteroid meeting a planet at great speed, breaking apart where air grew too thick. Computer power allowed researchers to watch its death blow frame by frame, albeit in simulation, and to see the blast radiating outward over forest in a way that matched both eyewitness reports and physical damage maps. These findings also settled older disputes. Why had no one found large rocks in the swamp? Because the body had vaporized entirely at altitude, and whatever pieces survived to fall were small enough to hide as dust in the soil. Why did the forest pattern have such strange directionality? Because the airburst's pressure had a center point overhead, pointing the trees like arrows away from it. Why did seismic stations as far away as England register the pulse? Because the explosion's scale was massive enough to send its echo down into the ground and outward for thousands of miles. Each question, once treated separately, now folded together into one explanation. Yet when the mystery feels solved, it often raises its most pressing question of all. If Tunguska was nothing more than a natural asteroid, then it was not unique. Events like Chelyabinsk remind us that Earth still crosses paths with small space rocks today. They may be rare, but they are not one-time accidents. Scientists liken Tunguska not to a freak event outside our system of knowledge, but to a dramatic example of what happens when space and Earth meet. Think about that shift in perspective. For almost a century, Tunguska looked like a deep riddle, possibly a singular moment that defied expectation. Now, after the work of modern models, it appears as something that, while rare, belongs in a pattern. Large objects colliding with Earth's skies, their fates dictated by size, speed, and structure. The forest that fell in Siberia has become a textbook example, no less astonishing, but now part of a broader truth about our planet's vulnerability. The value of computer simulation in this is profound. Without it, the numbers continue to drift. Some would sway low, suggesting a weaker impact. Others went high, suggesting something almost unimaginable. But by reconstructing the event starting from the known Chelyabinsk explosion, NASA's simulations in 2019 gave weight to one answer rather than many. They showed us how stone interacts with air, and how even at a size too small to survive as a whole body, an asteroid can still bring down thousands of square kilometers of forest in seconds. Let's take a quiet moment to imagine Tunguska not as a strange mystery anymore, but as a clear chain of events. A stone enters, pressure builds, the body fractures, and a fireball releases energy thousands of times more destructive than lightning or storm. Witnesses feel heat, see brightness, hear thunder, and are knocked to the ground. Trees fall, shock waves ripple outward, the rock disappears, and all that remains is flattened wilderness, glowing night skies across Europe, and soil holding strange dust. With simulation, these scattered parts form a seamless narrative. This clarity reshapes Tunguska from unsolved to a case study in planetary science. It is no longer the ghost of an unknown visitor, but an example of natural processes we now understand more completely. Yet that understanding does not lessen its weight. If a body not much larger than a school gymnasium can release the energy of hundreds of nuclear bombs, then the planet we live on remains quietly vulnerable. Tunguska is not forgotten, and Chelyabinsk is not dismissed as coincidence. Together, they mark a pattern that continues into the present. So while older generations wondered endlessly what the visitor over Siberia had been, today we can say with quiet certainty, a stony asteroid between 50 and 80 meters across, releasing 10 to 30 megatons of force in an airburst about 6 to 9 miles above the ground. That single picture captures the blast, the patterns in the trees, the shaking of the soil, and the silence of a landscape without a crater. It is no longer a riddle for imagination alone. It is a known chapter in the continuing story of Earth and the cosmos around it. And with that knowledge comes a sobering question. If Tunguska could happen once, and Chelyabinsk showed us it can still happen today, then how often should we expect the skies to open again? Was Tunguska a rare, almost impossible event, or is it part of the pattern of life on Earth, something that we can quietly expect over time? For many years, people leaned toward the first answer. They imagined the Siberian blast was a freak accident, the kind of thing that could only happen once in 1,000 years. It came from a time when little was known about the number of objects quietly circling near our planet, and when even meteor showers seemed less like scientific events and more like wonders in the night sky. That sense of rarity placed Tunguska almost into legend, a destructive marvel so out of the ordinary that it was unlikely to repeat within the memory of civilization. But in the past few decades, the picture began to shift. With wider surveys of the sky, telescopes scanning from Earth, and spacecraft looking outward, scientists gained a clearer sense of how many small asteroids share our region of space. Rather than one in 1,000 years or longer, the estimates for Tunguska-sized visitors moved closer. Objects between 50 and 100 meters across, the scale thought responsible for Siberia's morning fireball, may approach Earth more often than anyone once dared to imagine. Every few centuries, chances rise that a rock of that size could visit again, not in deep stretches of time, but within scales that press against human history. This subtle change in perspective tells us something important. Tunguska did not stand alone. It may instead be one example in a sequence that unfolds, not often, but often enough to watch carefully. Imagine yourself at the start of the 20th century, hearing reports of flattened forest in Siberia. The first thought would be, of course, that such a blast holds no place in normal earthly life. Remote, strange, out of reach, perhaps even myth. Now compare that to the early 21st century, when people in Chelyabinsk looked upward and saw the morning sky blazing with a fireball. That event was captured on countless cameras fixed to windshields, showing the bright streak, the flash, and seconds later, the shockwave. Windows across the city shattered inward, factory roofs twisted, people staggered in confusion. No crater, no large fragments, only an airburst once again, smaller than Tunguska, yet strong enough to injure thousands. In that moment, the idea that these events belonged only to ancient history ended. Chelyabinsk reminded everyone that space is not far, and impacts do not live only in textbooks. Take a deep breath and let the thought settle. The world had waited a century for another clue, believing Tunguska was a near impossible accident, and then, in 2013, another asteroid slipped silently down until it broke in the atmosphere. This is why modern surveys and models matter. They let us see Tunguska no longer as a once-in-a-lifetime freak, but as the larger face of something we already know happens more often than stories once admitted. The way estimates change is not through sudden revelation, but through careful watching. Near-Earth object surveys keep count, recording each faint point of light against the stars, calculating orbits, projecting possible futures. As the catalog has grown, the numbers reveal how Earth moves not alone in safe emptiness, but within a crowded neighborhood. Thousands of asteroids large enough to cause local damage share its space. Millions of smaller fragments lie untracked. Most will never cross our path, but some will. The frequency of these meetings becomes clearer only as our records grow, and with each survey, the scales of probability shorten. Where a century ago we thought Tunguska belonged to myth, today we see it fitting into natural cycles, spaces of centuries rather than millennia. What makes the matter pressing is not just the large events, but the smaller ones. A rock 30 meters wide may not destroy thousands of square kilometers, but it can still shatter glass across a city, start fires, and bring panic. Tunguska was immense, Chelyabinsk smaller, but both remind us of the spectrum of what can arrive from beyond. Small events surely happen more often. They may flare in the sky unnoticed above the ocean. They may burn through the atmosphere before striking ground, or they may ignite as flashes noticed only on sensitive instruments. The unpredictability is part of the truth. These events do not follow a visible schedule. They arrive when they arrive, silent until seconds before they become light in the air. Let's take a moment and imagine that uncertainty. Earth rotates calmly, days and nights pass without incident. Then, out of a clear sky, a fireball appears, brighter than the sun, breaking apart with thunder, releasing waves of heat and sound. Before anyone had thought of planetary defense, such an event would simply become part of the story. First confusion, then rumors, then years of speculation. Today, with networks of telescopes, we can at least map more of what circles near us. We cannot stop every fragment yet, but awareness itself marks a step forward from ignorance. And so, reassurance lies not in denying frequency, but in accepting vigilance. Humanity is no longer watching blindly. We track hundreds of thousands of objects. We measure their paths, and we refine those paths as more data arrive. Alerts are stronger, observations constant, and international cooperation deeper than it once was. It does not erase the risk, but it softens the fear by shifting mystery into prediction. What once was unseen now passes beneath watchful care. Tunguska, in this light, gave more than a mystery to resolve. It offered a warning, pressed into the soil and the flattened forest, that the skies are not always calm. That warning placed itself in scientific memory, reminding each generation not to trust emptiness, but to prepare for its sudden breaking. When modern calculations point to impacts every few hundred years, they echo that message. Not impossibly distant, not wholly unique. Rare, but part of the pattern of life on Earth. The Chelyabinsk fireball stands as its companion, a kind of echo in miniature. By being recorded and measured in real time, it turned possibility into certainty. Not a legend, not a guess, but evidence caught on film by thousands of ordinary lives. It drove home the point that Tunguska is not alone in history. It is part of a chain, stretching behind us and before us, each link waiting to appear without ceremony. That chain is fragile only in its mystery. As knowledge builds, links grow clearer, and what seemed like distant myth becomes present truth. Allow your thoughts to rest on this. If Tunguska had struck near a city, the consequences would have been unspeakable, far beyond forest flattened. But it chose, by chance, a remote wilderness. That chance spared humanity a disaster, yet gifted knowledge instead. In this sense, it became both omen and teacher. Its lesson is not to fear endlessly, but to recognize pattern, to admit possibility, and to prepare rather than ignore. Estimates today suggest Tunguska-scale events arrive perhaps every 3 to 5 centuries. That range is not comfort alone, but neither is it cause for constant fear. It is not daily, nor monthly, nor even something most people will ever see in their lives. It is instead one of those truths that remind us we live on a planet open to space, where the line between calm skies and fire from above can be crossed on rare mornings. Knowing this does not condemn us to dread. Instead, it guides us to build awareness, instruments, and readiness. This is where the true gift lies. Because humanity is awake to the skies in ways our ancestors were not, the risk becomes manageable. Space agencies coordinate. International groups share data. Telescopes sweep the dark steadily, mapping paths with precision. Every asteroid added to a catalog is one less unknown hiding in silence, and with each day, prediction grows softer and steadier, reducing uncertainty and pressing fear aside. In the end, Tunguska's great value rests not only in its physical mystery or its solved science, but in the reminder it leaves about time and scale. It shows us that cosmic accidents may be counted not in immeasurable ages, but in patterns that touch centuries. They are rare by the measure of human life, but not impossibly rare by the measure of civilization. This fact changes nothing about the universe, but it changes everything about how we face it. Let's take this final thought into calm reflection. Tunguska was not a singular freak occurrence, nor is it a constant danger. It rests in the middle, rare but real, distant but not absent. From this balance comes no reason for panic and no room for denial. There is instead only the steady truth that rare events can happen, that preparation is possible, and that watching the sky is part of what it means to live wisely on a planet open to space. It is in this quiet space between fear and reassurance that the idea of planetary defense took root. For if we know Tunguska can happen again, and Chelyabinsk proves it has already happened recently, then we must admit a role in preparation. And from that simple admission, drawn out in flattened trees, glowing skies, and camera footage, an entire branch of science began to grow with one purpose: to keep watch, and when possible, to protect. How did a single morning in the Siberian wilderness grow into the seed of a field now known as planetary defense? At first, Tunguska was seen only as mystery, a puzzle of trees knocked flat and skies glowing strangely. Yet, as the decades turned, what began as confusion shifted into something more practical. The question was no longer only, what happened, but, could this happen again? And if so, how could we protect ourselves? That subtle change in thought opened the path from curiosity to preparation, from looking back at what was lost to looking forward at what could still be saved. Think for a moment about the contrast between 1908 and now. In that year, humanity did not have aircraft flying across continents, let alone satellites orbiting above. Radios reached only short distances, newspapers still carried information slowly, and no one had the means to see an asteroid approaching from the dark sky. If the Tunguska object had shifted its path by a few hours and exploded above a European city, the damage could have rivaled the losses of a modern war. And yet, people living then would have had no warning, no chance to prepare, and no tools to protect themselves. Everything would have fallen into destruction without reason or defense. Today, however, the situation has changed in quiet but profound ways. Humanity now watches the night with sky surveys, wide telescopes mapping the faint movements of near-Earth objects. Observatories track these small wanderers, updating their paths with each passing year. And more than that, an entire office within NASA has been created with one goal: to keep watch and plan ways to prevent disasters before they arrive. It is called the Planetary Defense Coordination Office, and its existence sums up how far we have come since that morning in Siberia. This office does not limit itself to study alone. Its purpose is to find answers in the present and prepare interventions for the future. Let's take a moment to imagine the difference. In 1908, all that could be done was to measure fallen trees after the fact. In recent years, however, scientists have moved from measuring history toward shaping outcomes. The Planetary Defense Coordination Office works across nations, learning how asteroids move, what they are made of, and how they might one day be shifted or slowed. No longer is the story of Tunguska only about helplessness before surprise. It also becomes the reason for building systems that carry the possibility of direction and choice. The contrast between eras becomes clearer when we look at missions such as DART. In 2022, the double asteroid redirection test was carried out as the first real attempt to change an asteroid's path. A small spacecraft, guided across millions of kilometers, was sent not to observe, but to collide intentionally with a minor asteroid moon named Dimorphos. The impact was not violent by cosmic standards, but it showed something remarkable. The orbit of Dimorphos shifted. For the first time in human history, the movement of a natural body beyond Earth was altered by deliberate design. This test was not about saving the Earth in that moment. It was about proving that subtle change is possible and that prevention is no longer only a dream. Imagine how powerful that knowledge feels when set beside Tunguska. Then, forests fell with no warning. Now, humanity has reached the point of sending a craft across space to nudge a rock off course. It highlights a movement from powerlessness to a fragile but real capacity to act. The lesson of Tunguska is therefore not just about the past event itself, but about what it sparked. the drive to imagine solutions, to send missions, and to turn fear into preparation. Another mission, Hera, continues this path. Sent by the European Space Agency, Hera will follow up on the DART mission, examining the crater created by the impact and measuring the details of orbit change. Its purpose is careful, to learn how well redirection works, not in theory, but in practice. Numbers on paper can only go so far, but witnessing real results gives future planners tools and confidence. To have one spacecraft strike and another examine is to begin the process of turning defense into a consistently tested reality. Let's pause here. Take a deep breath and imagine Tunguska again, the sky opening in brilliance and the silence afterward. Compare that vision with the calm precision of a small spacecraft adjusting an orbit millions of kilometers away. Two moments, separated by a century. One born of helplessness, the other born of careful planning. The connection between them is not accidental. It is Tunguska's memory that helped encourage the spirit to prepare. Even governments now treat the risk differently. What was once hidden in myth or argued as unlikely has become part of formal policy. Asteroid hazard is not consigned to fear or speculation. It is written into space program goals and funded through national budgets. The reason is simple. Tunguska is proof that natural disasters from the sky are real, not theoretical. And if something has happened once and again in Chelyabinsk, then preparation is logic, not luxury. The policy shift means that when telescopes track a new near-Earth object, it is not only scientists who watch. Decision-makers look too, aware that protection measures are possible if planned with foresight. In this spirit of awareness, an international mark of remembrance was created. On June 30th, the very anniversary of the Tunguska blast, people across the world observe International Asteroid Day. It is not an occasion of fear, but of recognition. Through events, talks, and public gatherings, people share the knowledge that our world is part of a broader system, one where rocks and ice still pass near our path. By pausing each year on the day of Tunguska, memory becomes guidance. It says quietly, awareness is better than surprise, preparation better than disaster. Let's take a moment to see this gently. A remote swamp in Siberia, once shaken with fire and thunder, has become the cause for coordinated global reflection. What was once known only by scattered witnesses has become the starting point of international cooperation. In this way, Tunguska's legacy stretches far beyond the trees it flattened. It pushes into space missions, science budgets, and shared calendars. It has become part of policy and culture, not just myth. All of this shows something about the journey of science itself. We begin in confusion, feeling powerless in the face of an unexplained event. We struggle with wild ideas and speculative theories. Yet, over time, patience builds evidence, and evidence builds action. From Tunguska to the Planetary Defense Coordination Office, from flattened trees to International Asteroid Day, we can trace the line of discovery's quiet rhythm. The mystery that once felt eerie has transformed into plans, technologies, and shared commitments. The silence of forests knocked to the ground has translated over a century into a preparedness for skies watched and engaged. Even so, this story is not one of simple triumph. The risk remains real, and the power to prevent disaster is still fragile. A mission like DART is only the beginning. The distance between testing redirection on a small body and preventing a city-scale disaster is wide. But what matters is the direction of movement. 100 years ago, no such path existed. Today, it does. And by walking it step by step, the unknown becomes less threatening. Think of it this way. Tunguska could have remained a legend, sparking fear without guidance. Instead, it became a case study, written into science and translated into action. Knowledge of the event now ripples outward with real effects, missions, offices, and international days of awareness. This is the quiet transformation of mystery into progress. As you take this in, allow yourself to see that the path from eerie suggestion to practiced planning is itself remarkable. It shows how even destruction can become a kind of gift, pointing us toward wisdom. Tunguska flattened trees but spurred thought. It rattled the earth but planted seeds for preparation. It terrified witnesses but gave future generations motivation to act. From silence in a swamp, a global science has grown. So from one morning in Siberia to spacecraft striking asteroids millions of kilometers away, the thread remains clear. Tunguska was not only an explosion in the sky, it was the beginning of a lesson. It carried the simple truth that our skies contain surprises, and that knowing them changes everything. Today, we can watch, measure, plan, and even act. The journey is not finished, but its direction is steady. From mystery to memory, from helplessness to control, the story of Tunguska has become the first chapter in the long history of planetary defense. And with that, the silence of flattened forest leads us gently into a closing thought. The strange, terrifying blast above Siberia has become a reason why we live now, not only in fear of the skies, but with preparations that bring calm. From eerie fire to measured safety, it shows how science turns darkness into light, and how one disaster shaped the way we guard our shared world. Tunguska today is more than a Siberian mystery. It began with an airburst that flattened forests but left no crater, a riddle that resisted answers for decades. Over time, patient science uncovered microscopic spherules in the soil, weighed ideas like Lake Checo, modeled explosions with modern computers, and compared the Great Blast with Chelyabinsk. What was once only confusion slowly became understanding. Its legacy is practical as well. The mystery helped lead to planetary defense programs, the PDCO's Steady Watch, and even the DART mission proving deflection possible. If you found this calming journey meaningful, consider subscribing for more gentle science stories. And now, as the forest regrows and science quietly watches the skies, may you rest with the comfort that even great mysteries can guide us toward peace and preparedness.